All right, so now when you are talking about half-life of a radioactive element and the like, so first of all, we need to understand the law of radioactive decay. What is the law of radioactive decay? Or now when you say decay constant, what is decay constant first of all, and what is half-life? Now half-life is defined, all right, as the time it takes for half of a radioactive atomic nuclide to disintegrate or to decay to its half of the original value. Is the time taken to disintegrate a radioactive or atomic nuclide to half of its original value. So the symbol of half-life is T a half. All right, that is what half-life is. The time it taken, all right, for a radioactive element to disintegrate to half of its original value. So you have your n is equal to n naught multiplied by 1 over 2, or the final number of atoms is equal to n naught over 2. Then your T is equal to then T a half. All right, that's what we have in half-life. All right, this half-life, the time it takes for half of a radioactive atomic nuclide to disintegrate or to decay to half of its original value. Then another thing, all right, is what we call decay constant. All right, but before decay constant, I want to show you or talk about the law of radioactive decay. Now, the law of radioactive decay, all right, states that the rate of decay of radioactive element per second is proportional to the quantity of material or the element that is required in a given time. All right, the law of radioactive decay states that the rate of decay of radioactive element per second is proportional to the quantity of the material or the element that remain in the given time. So if I want to talk about that now, I have my rate of disintegration per second, dn over dt, all right, is proportional to the what? To the element that disintegrated. That is n is the mass of the element. So I have dn over dt because it is the thing we have introduced a constant, and my constant is the minus lambda n. Lambda is the decay constant, all right, which is what? The constant here. Then you have minus. The reason minus is there is because it is decreasing. As you are disintegrating the substance, it is decreasing with respect to time. So you have, so it's supposed to be lambda n, but because it's decreasing with time, you have dn over dt is equal to minus lambda n. So this one we have as what we call disintegration per second. So dn over dt in that place is what we call disintegration per second. So this is what the law of radioactive decay says. All right, the rate of disintegration per second is directly proportional to the what? Number of atoms on the element disintegrated per, all right, or required in that concept. So for that, our dn over dt is equal to minus lambda n. If that is the case, so we are going to be looking at how to use that to prove our value for n, because your n, all right, is supposed to be n naught, all right, inverse of minus lambda t. So let's prove that. So from my dn over what over dt is equal to minus lambda n, which I said this one is called the disintegration per second. So I'm going to be having, if I move t to the other side, I have dn, all right, over dt, all right, minus lambda n over 1. So if I move it, I have dn is equal to minus lambda n, all right, dt. Let me divide both sides by n. So I have dn is equal to minus lambda n dt, then over n and over n. So this one has gone with this. Then I have dn over n is equal to minus lambda dt. All right, if my dn over n is equal to minus lambda dt, what I'm going to do is that I will introduce my name, all right, if you find the integral of that. So you have integration of n to n naught, all right, into change in n over n, all right, is equal to, because this is transfer to time, I have integral of time to 0, and I have minus what? Lambda dt, which minus can be at the other side. So what's going to happen is that I'm going to be having, if I integrate, I have what? Ln n, all right, over n naught, okay, then it's equal to, so I have minus what? I have minus lambda lambda t, all right, lambda t, because I've integrated. So ln n over ln n naught is also ln n minus ln n naught, all right, which is equal to minus lambda t. Now, if this is the case, so I'm going to be introducing a logarithm of e to the both side. So if I introduce a logarithm of e to the both side, once I have ln n minus ln n naught is equal to minus lambda t. So, and it is also division. So I can rewrite it to be ln n over, okay, I can do something of this nature, all right, everything is equal to minus lambda t. So let me introduce the logarithm of e to the both sides. So I'm going to be having log e at the left hand side and log e at the other side. So I'll cancel a value out so that I can have my value suspended. So I'm going to be having at the end of the day log e, all right. Then what is left? Lane n over n naught is there, all right, is equal to, I have minus lambda dt. So I'm supposed to introduce log e to the both sides. So I have log e here also. So log e cancel log e, all right. If log e cancels log e, what is left? N over n naught is left. So I have n over n naught is equal to, this log e has gone with log e with the lane. So you have what? Minus lambda t, all right, and you have e here because you have the, if this lane moves to the other side, if you change to the inverse of lane, let me do it accurately. So this lane log e has cancelled. So you have lane n over n naught is equal to minus lambda t. So you have lane n over n naught is equal to this minus lambda t. If this lane is moving to this side, all right, you are going to be having n over n naught is equal to minus lambda t over lane, and the inverse of lane, all right, is given to the e, this e. So you press shift and lane your sign calculator. So you now have n over what? N naught is equal to e, then you have what? Lambda minus lambda what? Minus lambda t. So if this n moves to the other side, this raised to power minus lambda t. So you have n, this over 1 over n naught is equal to e raised to power minus lambda t over 1. Then you have, multiply, you have n is equal to n naught into e raised to power minus lambda t. Alright, this is what you have as the what value of the what final number of atoms to the initial number of atoms of that what radioactive element. So that is basically how to prove your final number of atoms. Alright, I'm still going to give us other values that we can use to find or factor the things out. So aside from that, we can also by that prove our radioactivity or radioactive decay, because we said that half-life is the time taken, all right, for a radioactive element to decay to half of its original atoms. Okay, so and I said that in that like manner, what is going to happen is that your n is going to be equal to n naught over 2, and your time taken is going to be t a half. So if you introduce that, recall this equation. Let's say this equation 2, and let's make our dn over dt. dn over dt is equal to minus lambda t, all right, as equation 1. That is disintegration per second. So what is going to happen if I recall this? If I recall my equation 2, recall equation 2, or recall n is equal to n naught inverse of lane raised to power minus lambda t, I'm going to be having, anywhere I see n is now n naught over 2 in half-life, all right, is equal to, so anywhere I see okay, I have n naught here as well, then I have e minus lambda. Anywhere I see t is t a half in half-life, so I write t1 over 2 in that place. Okay, that's what I'm going to be having. So if that is the case, the same thing I did is what I'm going to replicate. So that n over 2 or in that place is also what is given as, I can also write as 1 over 2 n naught is equal to n naught inverse of lane minus lambda, then my time taken has come to t a half. So I will find the what, the logarithm of that. Okay, so that 1 over 2, my n naught can go with n naught, so I now have 1 over 2 left, all right, which is n naught is equal to n naught inverse of lane minus lambda t a half. So this one has gone, so I have 1 over 2 is equal to inverse of lane minus lambda, then I have t a half in this place. So this 1 over 2 is also 2 raised to power minus 1 is equal to inverse of lane minus lambda t 1 over 2. So now if that is what I have, I can move, all right, the value to the other side by introducing a logarithm to that place. So if I introduce logarithm of e to this side, so I have log e 2 raised to power minus 1 is equal to log e minus lambda t 1 over 2. So there's another e here, inverse of lane before. So this e, this minus can go to this side. So I have minus log e, then 2 is left, is equal to log e, then inverse of lane raised to power minus lambda t 1 over 2. Okay, so if minus has gone, all right, lane has gone to that side too, what's going to happen? What's going to happen is that I'm going to be having my final value to be log e2, because minus and the other minus will go away, all right, if it moves to that side, if you apply the laws of logarithm. Okay, so what's going to happen is that I'm going to be having log e then 2, all right, minus log e2, is equal to, I now have minus lambda t I have, then I have log e and under what e. So this one has gone, minus go with minus, then log e has gone with log e. What is left? 2 is left is equal to t I have multiplied by, that is lambda t I have. So I have this at the end of the day. All right. Now that log e, if you find log e in your calculator, all right, it's supposed to give you log e2 is supposed to give you ln 2. Okay, so you're supposed to have ln 2 at that side. So that log e2 will now be ln what? Ln 2 is equal to lambda t I have. Then ln 2 is 0.693 is equal to lambda t I have. Where lambda is decay constant and t I have is the half life. So that means your half life t I have is equal to 0.693 over decay constant, or your decay constant, this equation 3, then your decay constant is equal to 0.693, then over half life over t I have, equation 4. That is the those are the equations of what? Of radioactivity. So you can use those ones to calculate. So, but basically in the last part, I want to show us how to calculate basically for your decay constant, um, which you can use this formula to calculate for. Then we can also show you how to calculate for things like count rate per seconds. All right, the Green ratio. I've given two formulas already, so I'll give the other equations of radioactivity in the next video.